Okay, let's see. Is everybody back pretty much? Yeah.
Yeah, ask if they can, someone can confirm. Can you hear us okay?
Hello?
Someone confirm that you're alive?
Yep.
Mhm.
Yes, yes.
Yes? Okay, good, thanks. Yeah, someone replied.
Okay, so I thought what would be an appropriate
There was a question if you want to just quickly.
okay.
Yeah.
If there's any.
It was if you have any input on the how the gas condensate regions change with time, especially how these regions look like if they become bigger or smaller as the reservoir is depleting, or if that matters at all.
Yeah, that's just trying to get a screen where I can see a little bit. Okay. Yeah, we'll definitely address that. I think today and tomorrow there may be some specific slides that have that point that's addressed, and then if not, then just make sure we return to it.
Yep.
I thought what would be an appropriate introduction to the condensate blockage, more in terms of cause and effect, quantitative impact, and so forth, is to actually move and go through this set of black and white slide presentations that were actually used when we presented the paper in 1995. I think they're certainly as relevant now as any time. So the paper covers the following description of the three flow regions in a gas condensate well, how to translate that into a gas rate equation using a pseudo pressure function, to verify the method, the three region method, comparing this rate equation with the pseudo pressure integral with fine grid simulations. And I will make the point that we consider fine gridded simulations where the near well geometry is properly discretized numerically to provide the correct answer in any given situation. So any method being used would need to be compared against that. It's not always easy to grid up complicated well geometries, but in this work here, we looked at three different well geometries: vertical unstimulated well, which is basically a radial concentric geometry, RZ, a vertical hydraulically fractured well, and then a horizontal well without hydraulic fracture. So these are, and that included the vertical anisotropy that you'd normally see in a situation like that. The application of the rate equation in coarse grid models, that was a result of having seen this observation during the forum a year earlier, that the producing gas oil ratio predicted by a coarse grid model could often and would often provide an accurate producing gas oil ratio compared with the fine gridded single well model. And then this issue of the fundamental relative permeability relationship that was originally identified and discussed in 1941 by Evinger and Muscat, the application of solution gas drive, but here being applied to the gas condensate case for near well region 1 behavior. And then the effect of directly and indirectly of critical oil saturation, IFT and velocity effects. The IFT and velocity effects addresses the capillary number dependence of relative permeability that was brought out in that 1994 conference, and the critical oil saturation follow-up to explain why the actual saturation itself doesn't really play a role in the blockage effect. And then as a result of all of this work to propose the design and interpretation of relative permeability experiments, that's something that was done on paper in this work, but which has since been implemented and run by commercial laboratories the last, what that would be, 25 years, basically. We started initially a joint industry project with, I don't remember how many companies, maybe 6 or 7 companies following the paper, who financed for 2 years laboratory experiments with what was then called ResLab, then became Weatherford, and then now is Stratum, to develop the procedures, test the procedures, make measurements on many different types of rock. And then that commercialized and has been used ever since. In fact, we're running 1 or 2 studies exactly of this type today, and they've been run pretty much around the world. So we'll look at that. So the simulations that were used in this study involve, for the most part, black oil PVT formulation, but based on an equation of state. We do some EOS-based compositional simulations, similar to the work by Fussell and at Amoco in '73. These are 2 gas condensates, one to represent a lean and one to represent a rich condensate. Maximum liquid dropout of around 2% for the lean and about 25% for the rich condensate, both with similar dew point pressures around 5,500 psi. The black oil PVT properties, most important is this solution oil gas ratio for the rich and the lean condensate. The formation volume factor, the dry gas formation volume factor, is plotted as its inverse to make it more linear with pressure. These are the oil properties, RS and BO for the rich and lean condensate. We see that in the case of, well, the rich condensate has non-monotonic BO as almost as for the lean case here. Viscosities, I believe, though I'm not sure, that these PVT properties were generated with a constant volume depletion method. So if we look at the magnitude of the oil viscosity in the near well region typically is around 0.1 to 0.2 centipoise for pretty much all the reservoir fluids we've seen anywhere, so it's fairly low viscosity. This gas-oil interfacial tension is used to calculate the capillary number, and what you'll notice is that in the range that's found in the region 1, pressures from 500 to maybe 3,000 psi, the interfacial tension doesn't get anywhere close to the very low values that you can reach in gas condensates near the dew point. That typically it's above 0.5 to 1 dynes per centimeter. So it's not a big effect on increasing the capillary number. I don't know that I've given if the equation is written. Let's see if I can get this to write or not. Let's see here. Goodness. Help me.
If you right click on the screen.
apologize. Let's see here. Tools.
You can take snapshot and put it in your text editor.
Yeah, that's probably the safest. It's easier for. Let me just do
You
that.
can't open in this Nitro Pro or whatever it's called.
Yeah. It is better what he's recommending for the. A second here. A little bit extra work, but that's okay. Let's get this formatting a little bit off. Yeah. Don't really need this picture in here to define the capillary number, but usually the velocity, the pore velocity of the gas phase, the viscosity of the gas phase over the gas oil interfacial tension. This really represents the basically the Darcy type pressure drop relative to capillary pressures. That's essentially what it's representing. So you see it's dividing by the gas oil interfacial tension, and you see the gas oil interfacial tension can get very, very low for near critical and just at higher pressures. So you would tend to see that increasing the capillary number significantly, but you never are in the near well region at these high pressures. So that basically about 1 millinewton per meter, which is certainly not a low IFT, is not driving the capillary number high. It's almost exclusively the gas velocity, because the gas viscosity is also typically in the range of 0.02 to 0.03 in this near well region, centipoise. So everything is controlled by this gas velocity, and the gas velocity, as I mentioned before, for radial flow is gas velocity is proportional with 1 over radius. So as you approach the wellbore radius, you're going to get the very highest velocities. And if you look at more linear light flow, which you would expect in a well that's got a hydraulic fracture, then you're talking about about 1 to 2 orders of magnitude lower than what you see near the wellbore. So, but anyway, this is what was used in looking at the capillary number effect. These were the default relative permeabilities. So we had a this is set A. There was 2 sets of relative permeabilities. We'll come back to that, particularly in relation to the critical oil saturation that's used. Now, one thing that I wish I could just figure out some way to.
And that you cannot open it with your manual. But that software is called Annotate.
Well, I know, but I usually do it in this version, so that's why it's bothersome that it's not.
What is this option? Here. This one? Now you're able to edit the text.
Okay.
And in comment, Curtis, you can try that. Go to the right there, comment at the top right. Comment, top right.
Here?
Top right. Comment there. Under, right under. Comment there. And then draw in markups.
Huh.
And then that pen, there should be a pen there. Draw for
Okay.
format.
And then
You go to the. You go to. Can you try to type on?
okay. It's like it's not.
What is this annotation?
So usually it's down here in the lower left.
Sorry, when you refer to velocity in hydraulic fracture wells, do you refer to the matrix?
Yeah, the matrix. Yes. Yes.
Velocity or the velocity within the fracture?
Yeah, the velocity in the hydraulic fracture itself will also really the relative permeability in the fracture and the hydraulic fracture will typically be close to straight lines anyway. So there's no gain, so to speak, from the capillary number effect. Okay. I'll give up on this. But so where these two cross, the KRG, KRO, that's kind of the first thing we look at in any study we're doing on condensate blockage when you show us your relative permeability curves. And the magnitude of that will typically, for all the rocks we've seen anywhere, is at worst from about 0.03, which would be down here, where the hand's at, to at most about 0.12, which Berea, Benheimer type. So any normal rock curve will be in the range, usually 0.05 to 0.1, the crossing point for conventional gas oil relative permeabilities. Okay, so the flow regions in the three flow regions, we've talked about this quite a bit. The steady state two-phase flow region with a constant flowing composition or flowing GOR. The region 2 condensate buildup region with single phase gas flow, and the region 3 single phase gas above the dew point. This is actually a saturation profile from a snapshot at a given time for one of the simulations. You can see the liquid saturation in the region 1 dropping down, and then more or less being in immobile oil saturation in the region 2, and then 0 in the region 3. Now, just to comment about this profile of oil saturation, and really it's oil mobility. This saturation profile is created such that as the saturated gas enters region 1, there's a pressure drop. Let's say every psi pressure drop from P star into PWF will contribute so many drops of liquid condensing out. Okay. As you lower the pressure, you'll get some liquid droplets condensing out. And depending if you're high pressure or intermediate pressure or low pressure, the number of drops of condensate coming out of the gas per psi pressure drop will change. And the mobility of oil and gas in this region has to be exactly such that no matter where you're dropping out condensate here, and in what amount, you have sufficient mobility that whatever condensate drops out of solution, it immediately gains mobility to flow together with the gas from which it came out with. So the gas that's dropping out cumulative is never being accumulated. It's always got just the sufficient mobility to drop out and then flow at the same velocity together with the gas from which it came. So that's why you get this profile of saturation and oil mobility. The gas rate equation, pseudo pressure function. This is again the surface product gas rate, a constant C. KH, log RERW, and skin. Now that skin will include basically any kind of well geometry skin. It can include damage, whatever. And then for the the gas mobility, there's actually two terms here. I've usually only been writing the first term, KRG over mu GVG. But in reality, this second term, I guess I'm just going to have to use the so the this is what I've been. This is actually the total gas mobility. This is the gas product flowing from the gas phase, and this is the gas product coming from the flowing oil phase. Remember, in the region 1, we've got an oil phase that's flowing as well. So basically, this is KRO over mu OBO. That's the oil rate in the reservoir in region 1 and stock tank barrels per day times the amount of gas it's carrying with it in solution, which typically this second term can be, usually can be neglected. The majority of the gas will be coming from the gas phase itself. Okay. The other thing about this term here, if you have a more complex geometry, then from your single well model with fine grid, what you should do is first do single phase gas flow. Okay. And then you can use the traditional gas pseudopressure P over mu Z. Okay. And you could run like a multi-rate test, or in this case, it's assuming Darcy flow. You basically get a gas rate from the model, you get a flowing bottom hole pressure from the model, and of course you have the average pressure from the model. And so you take these three for single phase gas flow, and you just use it in this same equation. But now the pseudo pressure is a single phase gas pseudo pressure, and you back calculate with your fine grid, description of the well geometry itself. You back calculate C, and then that's effectively the C that will be used for gas condensate, where the only thing that's changing will be the pseudo pressure treatment. Okay, so that's just a comment. This is for radial concentric flow. Now, to evaluate this pseudo pressure integral, we've got the PWF to P star, gas mobility with permeability, relative permeability dependence on pressure. Region 2, we still have gas relative permeability as a function of pressure. We have to figure out how to determine that, estimate that. And then region 3 is just the standard gas pseudo pressure function. Region 1 pseudo pressure, this is the same equation I showed you for the solution gas drive, except it's got this little rs times RP term. Otherwise, it's the same. That takes into account, in the Muscat equation, they do not consider condensate coming from the reservoir gas phase flow. They don't consider any oil, surface oil coming from the reservoir gas flow. Here, we're taking into account all contributions of surface gas and surface oil products. This gives us this equation here for KGKO as a function of pressure. RP, that's just the producing GOR. That's what's very important to get right. All the other properties are just standard PVT black oil type data. And then we get from the relationship of KRG to the ratio, we get the KRG as a function of pressure. Of course, we also get the KRO if you want to include the second term. Okay, any questions about this method of calculating the pseudo pressure in region 1?
I'm sorry, Curtis. I couldn't see where the pressure is calculated in this equation. So
where the pressure is calculated. So, yeah. Let me just take this in. Okay, so this region 1 is being evaluated from PWF, read, to P star, right? So we know both of these.
Mm-hmm.
And then we've got this gas mobility, which is a function of pressure. So what you simply do is that you set up a pressure table starting at PWF, any low pressure, discretizing it up to P star. So for each one of these pressures, you have all the PVT properties. I'm just going to write it PVT properties, which are a function of pressure. You get all those properties. That would be RS, little rs, BG, mu G, and so forth, mu O, BO. You get all the PVT properties. And then once you have those, we know the current producing gas oil ratio or the current producing oil gas ratio. We can then calculate the KRG KRO, right? Because that's the only thing that's entering. That's known. So we get that for each pressure in the table.
Mm-hmm.
So you're not calculating the pressure other than you do calculate that pressure, which is the dew point in your black oil table of the producing GOR. So if you got a producing oil gas ratio of 100 barrels per million, you look at your saturated black oil table for 100 barrels per million, the dew point's 3,200 psi. So that's the only, let's call it calculation or lookup of the P star. Then you just have to discretize it into pressures between these, and for each pressure you calculate PVT properties, the KRG KRO ratio, and then from the rel perm we get the pressure dependent KRG. This is the rel perm model to go from here to here. Okay? Is that clear?
Thank you.
Yeah. All right. Okay, so these are a series of KRG versus KGKO. For the only thing being changed here is pore size distribution. Now, what you see is that the easiest, I was just telling you that, you know, where they cross, basically that's where this is equal to 1. You can see that this, from the standard Corey, I don't remember what the exponents were on the saturation exponents, but you see these ranging from about 0.07 to about 1.12. And so these would be different types of rocks, okay, with different pore size distributions. Now, if you're going to do a sensitivity to different rock types, then you would change the pore size distribution, which changes the exponents of gas and oil according to the Corey equations, right? Okay, so the exponent n, g, and no, these are functions of the pore size distribution. That's according to Corey Brooks type model. And in addition to that, you would expect the possibility that SOR, or SOC as you want to use it, would also be, by the way, this thing here is usually given the symbol a little bit dangerous, same as mobility. It's usually given the symbol lambda for pore size distribution. So you would also think potentially that according to the pore size distribution and the connectivity of the pore sizes, that the residual oil saturation might also be a function of pore size distribution, but there's no fundamental relation coming from the Corey type equation. You might just say that if you got more a lower distribution factor, the likelihood of having a higher SOR, you know, maybe it exists, maybe it doesn't, but it needs to be determined experimentally. So if the SOR did change with pore size distribution, then all of these curves would change accordingly. But they would be changing because of the pore structure, the pore distribution, and the connectivity of the pores, which usually controls the residual oil saturation. Okay, so
Curry,
yeah.
Sorry. So, what then defines the difference between rich gas condensate systems, difference in the relative permeability, and lean gas? Because my belief was that for rich gas condensate, you would have higher SOR, or you would have much higher liquid dropout.
So I would say that there's very little likelihood that the endpoint saturation is a function of the richness of the gas condensate. For sure not. There would be no reason for that. It's a rock property. You know, the fluids are, so it's definitely could be related to pore size distribution and maybe, you know, rock type, but not the fluid, no.
Okay, but then why would for rich gas condensate you would have less KRG, KRO, and for lean gas higher?
Okay, yeah, so that we're going to get to, because if you look, okay, that's a good point. Okay, so when you see this equation here, okay, this is low for a lean condensate, right? and this is high, this here, that's the CGR. It's high for rich condensate. Agreed?
Yeah.
So that would mean for a rich condensate, this RP is low. You may not see it from this, but if you have a low RP, then the KRG, KRO will also be low when you make this calculation. In other words, if the only thing you change is you use 200 let's say 50 barrels per million, that would be 20,000 GOR. If you use 20,000 here, then you'll get, I'm sorry. Okay. If this is RP is low, then it's a high CGR. So if you use, apologize. Okay. A low gas oil ratio is a high CGR. So let's say 200 stock tank barrels per million. Okay. That gives 5,000 cubic feet per barrel. So if this is a low GOR, which would 5,000 would be a low GOR for gas condensate, then you're going to find that the KGKO at a given pressure is going to be lower than if you use a 50 stock tank barrel per million standard cubic feet. That would translate into 20,000 RP, right? This is 5,000 standard cubic feet per stock tank barrel RP, and this 50 barrels per million is 20,000 standard cubic feet per stock tank barrel RP. So in this range from P star to PWF, P star, let's say it's 5,000, either for a lean or a rich condensate, all the PVT properties might be the same, but when you calculate the KGKO for a rich condensate, a low RP, you're going to get lower KRG, KRO. And when you have lower KGKO, from this figure here, you're going to have a lower KRG, right? And this 0.1 is about as low as you'll get in a gas condensate. This would be something like a 350 barrel per million condensate. It might give you 10 to the minus 0.1. Okay? And if you have a very lean condensate, 25 barrels per million, then you're going to be up in, close to the 50, 100 range of KGKO. And then you're going to get a KRG that's much higher. So this splitting here is related to the relevant range of KRG, KRO ratio.
That's for the region 1, right?
For all of this is region 1 we're talking about. Exactly.
Yeah.
Exactly.
So that's, I think that was the confusion, because for overall system, if you have more CGR, then your KRO will be more. But for the region 1, this is the case.
Exactly. Yeah, this is all for region 1. It shows here. Yeah, exactly. Okay. Okay, so so we did this verification on the 3 different well geometries that I've mentioned earlier using fine grid simulation. Now, this figure is a little bit busy, but this is our main results figure, okay? The simulation, the fine grid single well simulation are open symbols. The proposed method, this is now rate versus time, okay, is the solid line. And the this last method is basically is not, it's just confusing the figure, but the last method basically says that if you do a material balance, a constant volume depletion in the material balance, meaning that the gas that you remove, the solution, the little RS, that you remove at a given pressure in the CVD test, if that's 50 barrels per million, you ignore region 2, okay? If you ignore region 2 and apply basically region 1 to the entire drainage area, then you get a much bigger blockage effect, and that's given by this dashed line, okay? So the dashed line on rate versus time is like the original Odell-Miller calculation. It's like the Evinger-Muscat calculation, where you assume region 1 is throughout the entire drainage volume. Now, if you use the actual producing gas oil ratio, which are the symbols here and open symbols here, and then from that, each time you get a producing GOR, you find what is the dew point pressure of that producing GOR. That defines P star. We now divide into region 1 pseudopressure integral and region 2 pseudopressure integral. So we have two regions, the more correct, by using this open circle, the correct producing GOR. And you can see the difference between the producing CGR from a fine grid model and the solution CGR from the CVD test. It's not very different, but it has a big effect on the rate time performance. You can see that here. Solid line versus the dashed line on rate is because you're using the wrong CGR in the pseudopressure approach. And the dashed line CVD CGR is basically using region 1 throughout the entire drainage area. Okay, so this is a radial well, the rich gas. This is a radial well, the lean gas. Okay, and again, the open circles, rate time from the model, from the fine grid model, from the 3-region model, and in the 3-region model, the proposed method, we're using the correct producing GOR here. And then this applying region 1 throughout gives you this much lower rate than the, it doesn't maintain any plateau for this example. Vertical fractured model, rich gas. Getting the plateau exactly right, and then it's slightly deviating here late. This is the horizontal well with a vertical permeability of 1/10 the horizontal permeability. Rich gas.
When you're saying simulated, that's with region 1?
No, simulated is a fine grid single well model. So everywhere it says simulated, it's a fine grid. You got a very fine grid. We're talking inches.
Okay.
The grids nearest the well are inches in size, and then they usually get larger as they go away from the well.
Okay.
So it's a very finely gridded single well model. So it's the correct answer. That's what we were talking about. The correct answer will always be a sufficiently refined single well model to actually capture all of the condensate.
Yeah. And then the dashed line for the GOR, that is if you consider region 1 throughout the well.
Yeah, it's just a CVD. It's your little RS.
Okay.
It's your little RS turned upside down.
Okay.
It's your 1 over little RS curve. And what you actually produce will always be somewhat leaner than that because of region 2. You're losing some of the condensate in region 2. That's why it's always a little bit. The difference here is due to region 2.
I'm sorry, Curtis. What I can see from the graphs is that proposed method is matching with simulated method. And as I could see from the graph as well, it means that you propose to use a simulated GOR value. So the GOR is going to be taken from the PVT sample that we took before, or what's the way forward?
Well, so here we're using the exact GOR from the simulated model. The proposed method uses the simulated GOR, which is correct. Okay, that's the correct GOR. The question is, and what I talked about before the break, is if you use a coarse grid full field type model, is the producing GOR of the coarse grid similar to the fine gridded GOR behavior? Okay, that's the question. We don't show that here yet. We're just saying if we use the correct GOR, then we're able to calculate that pseudo pressure integral correctly. So we haven't discussed at all yet, how do we get that correct GOR in a model?
Okay, but basically to sum up, it means that for our modeling, we shouldn't use a CVD measurements, we should use a PVT model.
Now, the CVD here is actually being calculated by an equation of state.
Okay, so it's also simulated GOR.
Yeah.
In some way.
Yeah, that's right. So it's, yeah, so I think, let me just try to, let's grab this. A material balance is basically equal to a single grid reservoir simulation. Okay. Nobody uses, I mean, instead of using MBAL, you could use a single grid for every reservoir flow unit, okay, in Eclipse or something. Now, for gas condensates, the CVD experiment basically says that oil mobility is equal to 0, right? And so if you assume, and if you built a one cell model of a gas condensate with normal relative permeability curves, effectively you would, in the single cell model run, you would never get oil mobility. So in this case, what you're saying is that the producing oil gas ratio is equal to the solution oil gas ratio from the CVD test, because there's no, that's a material, that's the most common material balance assumption for gas condensates. Okay, approximately. And it's generally okay within maybe 3 to 5%. maybe a little more than that sometimes. But that you see from that's the difference between these two numbers here, the circles, which is the actual producing GOR, and the CVD GOR calculated as 1 over little rs. So they're close. So in terms of recovery, of condensate, it's a reasonable approximation, okay, for recovery. So for condensate recovery, it's kind of an okay assumption. It's always the rule of thumb. It's the approximation that's okay. But when it comes to the gas rate equation, okay, the assumption of Rp being equal to little rs at average pressure, okay, basically is saying that you have only region 1 flow.
Yeah.
And that results into excessive blockage. That's what Odell and Miller showed from their work with that assumption. Fussell came along and said, no, the actual blockage doesn't look like that. And the reason is because of this small difference, the fact that Rp is actually going to be less than that little rs, because this region 2 exists. Okay? And the region 2 mobility from this region 2 is considerably larger than the region 1 mobility. So if you assume region 1 is everywhere, you take a big hit on the mobility of gas everywhere in the entire reservoir. Whereas if you include this region 2, then you maintain a lot of the mobility that's actually there.
At the expense of very small difference in the GOR.
Yeah. So what's okay for the recovery point of view is not okay for modeling the rate. Okay. And so the question is, how do you get the producing GOR correct without running a fine grid model? Because when we have a huge field and 100 wells, you can't have fine grid models everywhere. You have coarse grid models. Okay. I don't know if that's helping any, but so now we're going to talk about how do you apply this 3-region rate equation in coarse grid models, because that's really what we need. We need to do full field modeling, but we need to capture each individual well's condensate blockage accurately. And to use this 3-region model, you have to have at every time step a good approximation of the actual producing GOR. That's what you need. And so what we show is that the producing GORs from the coarse grid model are in fact accurate when compared with fine grid model. And then what we can do is say that if that's the case, then we can build the pseudo pressure function inside the simulator so that when we do well grid calculations, we take that into account and we basically compute the area of gas mobility dynamically. According to each well connection has a producing GOR. You can calculate that entire integral and get the area needed to calculate the relationship between grid cell pressure and bottom hole flowing pressure.
So you ignore the bottom hole flowing pressure from the full field model? Like it also, the full field model also calculates the bottom flowing pressure. You ignore it and you override it with some.
Yeah, but the flowing bottom hole pressure is not really, it's a more of you calculate it as constraint. When you include this, then it actually solves for the bottom hole flowing pressure, including that area calculation. That's just another part of the equations. So yeah, it's found iteratively, the bottom hole flowing pressure, but including the calculation of the pseudopressure interval. Okay, and then we also show that this well productivity context C can be used pretty much for any well geometry skin or whatever. And then to show that all of this works, because we didn't have access to the source code of Eclipse that was used, we actually pre-calculated the pseudopressure integral and implemented it as a tubing table. Okay? Because it's basically a function of the producing CGR and the pressure. So you basically got we could pre-calculate that as a tubing table to check whether it worked. So now you see here, the fine grid is the open circle on the GOR still, and the coarse grid treatment shows the GOR here, the solid line going through the coarse grid. So the coarse grid is the solid line GOR, and it's essentially going straight through the fine grid GOR. By standard method, that's basically using the, let's see here.
That's the CVD material.
Huh?
The CVD material balance that you were proposing, that you mentioned earlier.
Yeah, that's this is just the standard well treatment, the PI treatment without any pseudo pressure. It's without the tubing table. It's without the region 3 treatment.
Region 1.
Region 1, I'm sorry. Yeah. You ignore the region 1, and that's what we call standard. Okay. That's the simulation without any special. So basically you get, and this is a radial rich gas case, you can see that you get too much gas rate compared with the actual. Again, the coarse grid this is radial for lean gas. So we see the coarse grid and the fine grid GORs tracking each other quite closely. So the difference here is that we're now using an almost correct producing GOR from the coarse grid model. And it has a slight effect on how accurate the 3-region model is. But compared with the coarse grid simulation from without any correction, you have, basically you get twice as long the plateau. Coarse grid. Okay, so now we're looking at a vertically fractured rich gas condensate, and here the coarse grid size is 500 feet. We're still getting a quite reasonable prediction of the producing CGR compared with the fine grid model. We're getting the plateau length and the rate profile correct. This is the horizontal well. Grid size is 100 meters. There's vertical discretization in the horizontal well. Okay. So these were the results that basically showed that you could use coarse grid simulation to get the producing GOR, use the 3-region model to get the well, basically mainly the region 1 pressure drop correctly, and it would improve the description of the blockage. almost the same as a fine grid model.
So is there a possibility that this is the profile from the standard method can be matched with the proposed method by just adding a skin value?
You could add a skin value to exactly match that plateau length, but when you don't have a plateau, the thing is that it's changing in time.
Yeah.
That was the thing that the Amico study showed, is that they had this very complex blockage skin that varied with rate, drawdown, producing CGR, all these different things.
Okay.
Yeah.
But that's effectively what you're doing with that table.
Yeah, you're adding an extra pressure drop that is varying with time.
But it's changing with time.
Yeah.
It changes with the time according to the only variables that you really need to have, which is the producing CGR. Yeah. That's all you need. This is the producing CGR dependence.
Mind blowing.
So with these results, I think pretty much everybody saw that the potential for having a very simple solution built into the well calculation, and what you're doing is you're giving away to the normal the normal well calculation. If you've got a grid and you have a well that's connected to that grid, so this might be 100 meters by 100 meters by whatever, 25 meters, something like that, and we've got an average grid pressure that we solve for, and what we want to know is what is the correct flowing bottom hole pressure at a given production rate. Because you give a target rate, and if you say, if I want that target rate, what's the flowing bottom hole pressure? And the normal way to calculate that is you've got what's called a well index, which is just like our C, times pressure average grid minus PWF, okay, times the average mobility of the gas phase, basically, in that grid cell, just using the average saturation in the entire grid cell. This is the normal way to calculate the relationship between gas rate and bottom hole flowing pressure. So instead of this, the method that we proposed was to use the same well index, C, and then to calculate basically this integral from PWF to PG, okay, and this would be represented here by, so basically you break this in again you might break it into 1, 2, or 3 regions, even within a grid cell. So basically you have the three region model discretized to integrate. So it basically goes from PG, it finds lambda G, and we've got PWF. So it actually computes that function for a number of pressures between the grid pressure and PWF, and it calculates that function and integrates the function numerically.
And your P star will be somewhere in between PWF and PG.
Yeah, so the P star could be in here somewhere. It depends on the producing GOR. And this is now called GPP in Eclipse 100 and Eclipse 300. Okay.
You said 3 regions, but here on the graph we show from PWF to P star and from P star to PG. Where is the third region then?
Well, you may or may not have it. In theory, you could have all 3 regions. Your PG, your P star could be here, your P dew point could be there, and PG, the initial dew point could be there, and then PG could be greater than the initial dew point. It could have 3 regions, it could have 2, could have only 1. Yeah. You know, the RP will give you the P star, and then you'll compare the P star with PG, and then also with the initial dew point and so forth. So you, yeah. So that was the results that were provided to justify the implementation of the GPP type option. And then the next study was to look at how region 1 behavior is controlled by this fundamental relationship given originally by Evinger and Muscat. Saturation does not enter directly into the flow in region 1, but is established to honor this relationship. And only a very limited range of KRG, KRO affects region 1 for a particular gas condensate. Same curve that we looked at earlier. So this is an example where we took the original, or we took a set of rel perms, set B, and residual oil saturation, I'm not sure what it is. But you see clearly that the saturation rel perm curves are very different. But the relationship between KRG and the KG-KO ratio is exactly the same. They're identical. Okay. And here's the performance of the wells with the different rel perms. Okay. Now the saturation profiles in region 1 will look different, maybe also region 2, but the deliverability loss is identical. So now we're going to do something similar for the critical oil saturation. So here we take this KRO curve, and we just used different from 0 to 20. We just changed those. So what you see is that the KRG curve is identical, okay? And what that means is that the rank from between KRG, KRO ratio of 10 and anything lower, it'll be using this curve here. So the relationship between KRG and KGKO will be identical below a value of 10. Above a value of 10, it's going to start to change, of course, dramatically, depending on where you go here. But more or less symbol thickness difference between the three different extrapolations. So having the laboratory spend a lot of money to measure this critical oil saturation makes no sense. What you want to get is the actual, you want to get this behavior here in whatever the relevant range of KGKO is, 0.1 to 10, 1 to 100, or maybe through the whole range. That's all you really care about for getting the blockage region correct. And how it extrapolates far away from this region of interest, which is up here, doesn't matter. I remember that when we presented this at the forum, there was a guy at lunch from ELF. I think it was from ELF, yeah. We were having lunch and we sat next to each other, and he just literally refused that the critical oil saturation was not the major rel perm effect on blockage. And I says, I tell you what, if you can show me one example, send me a simulation or whatever, one example where this relationship here is the same, but the critical saturation extrapolation is different, that it has an effect on the rate time performance and everything, I'll send you a personal check for $1,000. That was a serious lunch. And I was serious. I said, I'll send you a check for $1,000 if you just send me an example. And of course, I never heard from the guy. Luckily, he didn't find an example. But about 5 years later, we were looking at a study by ELF on a Norwegian rich gas condensate field called Vale, V-A-L-E. It was a very, not a big, it was a quite small reservoir, but a near critical gas condensate. It was during Easter. We went down to Stavanger, and I took with me the data deck, the simulation data deck. You may not have even been born. And I think you were just born. And you were young, and I was babysitting, and so you were sleeping, and I was punching in these numbers. They had 5 sets of relative permeability. So I punched them all in, not the saturations. I punched them all in, and I plotted them as KRG versus KGKO. And I swear, okay, the 5 curves fell on top of each other. They were for different water saturations. So what they had done is they'd gone back and they'd found out that this was in fact the case. So what they did is that they decided to use this as the means by which they would normalize their relative permeability curve, so they would always get this performance because they had some data measured that said that this KRG versus KGKO relationship that they'd found, they wanted to honor that. So however they were going to adjust them for endpoints, they never wanted to leave. The 5 curves laid straight on top of each other. So the guy wanted my $1,000, but he didn't get them. And it was verification that they'd gone back, done the analysis, and this is exactly the type of normalization that we do in studies where we only have one rel perm curve at one water saturation, and then when you want to go to other water saturations, you choose the endpoint scaling such that you maintain this relationship. That's so. Anyway, that was a pretty strong.
So then this is the reason why your model in Eclipse is not really scaling the endpoints. How I got it.
Yeah, I'm not sure how
remember.
Eclipse does the scaling of endpoints. You might check, Singh might have a comment on that. Whether it has an option to scale such that you don't lose this relationship, I'm not sure. We have some special code that allows you to rescale rel perms to different endpoints, water endpoints, that maintains this this relationship here. Are you saying that you think Eclipse does the same thing or does not?
No, it's not. I mean, if we use the Whitson model, it's not really touching the endpoints.
No.
So yeah, now I understood why.
Okay. Yeah. Okay. Yeah. So that's okay. So then we on this here. Yeah, this was early attempts to look at the effect of IFT on capillary number dependence. Yeah, this is the oil viscosity difference between black oil and compositional. Now, this is just something to be aware of. If you see any differences between compositional and black oil for the blockage effect, then it must be, I think, related to the viscosity difference in the black oil and the compositional. Okay. So the final part of the presentation was this recommendation for how to design and interpret relative permeability experiments. So the idea was to do steady state flow tests for a limited range of mixtures of gas and oil that cover the relevant range of KRG KRO ratio, and without measuring any saturations. And then you can do one saturation measurement if you insist on having it tied correctly to the saturation measurement. This is optional. If you have a very rich condensate, then you may want to get a single measurement of KRG at end saturation. And the reason for that is the following. So the Corey type equation of relative permeability will always give something that drops down. Maximum decrease in relative permeability will come at the endpoints. Okay, so this will drop down and then it'll slowly, move something like this, then over here towards that. So the Corey equation has this inherent rapid drop in KRG. And if you have a rich condensate, then your region 2 saturations will be here. Okay? Less than 30%, but there. If you look at most of the measurements we've been involved in the last 25 years, what you tend to see is gas, relative permeability gas, changing very slowly. And it actually has a maximum drop here that may end up coming back down, something like that. But it's got more of an S-shaped curve. Now there's correlations that are published that have this shape. Karichi has one. There's the
LET.
LET is one from Statoil. And then, so you basically got Karichi. Is it LIT?
LET.
LET, some Statoil folks. And then I think probably the first one might have been Arco by Gerald. I'm not sure if it was the first, but Gerald, Aaron Zick was involved in that as well, but not as a co-author. That give equations that give you this kind of S shape. My point is that if you have a very rich condensate, the difference in relative permeability in the entire region between 0.7 and 0.4 will have not a first order effect, but an effect. Okay? And so what we say is that if you have a richer condensate, then you try to make one KRG measurement with the saturation, with only gas flowing below the critical saturation, and make sure that the curve that you fit to the steady state experimental data, KRG versus KGKO, also that it will honor this one saturation point that's in region 2. So this is the Corey, and these over here are. So that's the purpose of this last statement. For gas condensates, higher liquid dropout, a single phase KRG at near or close to the SOC or whatever, to get an idea which of the models is the best suited for region 2. Okay, that's now tomorrow we're going to discuss a little bit more of the details of that experiment. And so how do you establish what is the range of KRG, KRO that's relevant for a particular reservoir? So this is the way we do that. So we take the original reservoir gas, and what's the design range Are we past the hour and a half?
No,
Okay.
we still have 4 minutes.
We have a design range
Well, we
for
didn't pass it. That was a
K
question,
or
right?
G. No, that was the question. K or O. And so what's done is that you simulate a CVD of the initial gas. And that provides you 4 to 5 approximate well streams that you expect to be produced during the life of the well. Okay? And this is at approximately the same average pressure. So when the average reservoir pressure is 3,000 pounds, if we go to the CVD test, then the CVD composition at 3,000 pounds will be a reasonable approximation of that well stream composition. So we create 4 or 5 approximate well stream compositions, including the initial one. And then we do a CCE of each of these compositions to generate a table of relative oil volume, gas viscosity, and oil viscosity for that particular, for each mixture. Okay. And then the equation that gives K or G, K or O is 1 over VRO minus 1 mu G over mu O, where VRO from the CCE that's the oil volume over the total volume. So from these PVT calculations for each of these 4 or 5 mixtures, we can create a plot of KG/KO ratio versus pressure. And that's shown here. And the region of interest for region 1 is out to about 2,000, 2,500 pounds, this region here. So you can see that the original gas has a ratio of a little less than 1, maybe 0.5, about 1.5, maybe 3, and the leanest condensate, with it just depleted down to here, has a value of 10. So here we want to have measurements from a 0.5 to a value of about 10 or 20. A very limited range of KG/KO. So we want to do 4 or 5 flow tests exactly with this range. Steady state flow test. So that's the strategy for, we'll come back to that tomorrow when we talk about the experiment, but that's the strategy for determining this range. And it's usually very narrow. Okay, it'll always be between 0.5, 0.1, 0.5, and 100. And it's usually a narrow slice of that. Okay. Again, we're going to return to this tomorrow when we talk in more detail about the experimental procedures. We also recommend using reservoir conditions, and instead of reservoir fluids, we use synthetic fluids that mimic the reservoir fluids. This will all be discussed tomorrow. Okay. So any questions before we take a break? So this paper.
One question.
Yeah.
At which pressure we
evaluate this range? PWF min, yeah?
Yeah, the PW min, that's exactly this.
Okay.
Yeah. Yeah. So here for the lean gas, you can see we're interested in a range from 5 to 50. And that's for the whole life of the field, of the well. And as you can see here, that the blockage effect is getting less and less as we get a leaner and leaner fluid being produced from the reservoir. So. Okay, I think we'll stop there. And